All right. Good evening. So we're doing the Voltaic cells masterclass this evening. So I'm going to get started without further ado, and hopefully this will open to the right page. Fantastic. So if it's open to the right page, at this point you should be able to see both the cell potential table on the one side and just to the right side, so you can see all the bits, as well as you can see the information here. I'm going to be rather nice, and if we need to work out the cell potential, I'll in fact write up the formula. Well, I'm not going to write it up here. If I write it up here, it's going to disappear every time we change to a new page, but we're going to be working from here. All right, so we're going to start with the only multiple choice that I prepared. So there's only one multiple choice for what we're doing, and it's from one of the past papers, and it basically says, consider the reaction represented by the balanced equation below. In the above reaction, copper is, you've got to decide if it's the oxidizing agent or the reducing agent, and therefore if it is oxidized or reduced. So I'm going to pause sharing straight away, and I'm going to give you an opportunity almost immediately to get into answering the question. All right, please go for it. All right, when you get to your answer, I'm going to ask you to please give me a thumbs up to tell me that you've got there. All right, so for most of you, I think this was rather nice and straightforward, but let's see. Okay, fantastic. I think everybody's given me a thumbs up so far. So if I continue here, I'm just quickly moving that so that's in a decent place. There we go. All right, so my answer here was D. I took copper and remembered that since it was an element, its initial oxidation number was 0. It goes to be 2+, which they show you there. So in this case, it's going to lose negative electrons to become more positive. Since it loses electrons, oxidation is loss, reduction is gain. It is oxidized. Therefore, I needed to find an option that says oxidized. I probably could even have cheated here because it's not an oxidizing agent if it's oxidized. It's a reducing agent if it's oxidized. Can I quickly ask who got that correct? Thumbs up if you got it correct. Fantastic, well done. I must admit I did kind of expect that you might get that one right, because it is the one that I think you are probably most prepared to answer. All right, moving on to the next question. The next question is a little bit longer and a little bit trickier. I also suspect I may struggle a little bit with space. Can I quickly ask, before I go any further, can everybody read the actual writing on that? Can everybody read the writing that I showed you there? Okay, fantastic, because it is a little bit small, but hopefully not too small. So I'm going to run you through the questions, and then I'm going to tell you how far we go before I pause and we both work it out. So all of your questions tonight are going to be question 8. That's where it is in the paper. And it says, a standard electrochemical cell is set up. You must remember that there's certain conditions that are connected to it being standard. Using a standard hydrogen half cell, you remember the standard hydrogen half cell is the cell that we compare everything against. And a standard XX2+ cell. Now, X is not on your periodic table, so this is something we're going to have to look for. A voltmeter connected across the cell initially registers 0.31 volts. This is your E theta cell. Okay, that's what that value is. So there's your hydrogen gas. It's got a bit of a different electrode because it's got the gas coming in, and we've got our aqueous solution at the bottom. We don't know what X is. All that we know is that it must be able to form 2+ ions, which limits us a little bit, but not enough for us to be able to be sure. So question 8.1 says, besides the concentration, write down 2 conditions needed for the hydrogen half cell to function under standard conditions for 2 marks. Please remember, be specific. And then question 8.2 says, give 2 reasons besides being a solid why platinum there is able to be used as an electrode in the above cell. Please, we're not assuming that X is platinum. That one clearly we're told is platinum. So I'm going to pause just briefly for a few, well, minutes maybe, and ask you to write down your answers to those two questions. Go for it. All right, can I ask, as soon as you've got all, well, technically there are 4 answers because it's 2 questions with 2 answers each. Once you've got all of those, give me a thumbs up so that I can see. Okay, brilliant. Okay, fantastic. That looks like the majority of you. You may find that you can only come up with half of each, and please rather write down one of the 2 than nothing. All right, so I'm going to share this already because I've got quite a large number of questions for tonight. And I want to make sure that we get through as many of them as possible. So the 2 conditions were that you needed a pressure of 1 atmosphere for gases and a temperature of 298 Kelvin for everything. Please, I wouldn't just say pressure and temperature. I know that they said concentration, but that was because they weren't yet giving it as an answer. So I would say here, to get your marks, you can't just say constant or standard pressure and standard temperature. You have to tell me what the values are. So pressure of 1 atmosphere or 101.3 kilopascals, and a temperature you can either write as 298 Kelvin or 25 degrees Celsius because they're equivalents. Then for 8.2, give 2 reasons besides being a solid why platinum is suitable to be used as an electrode in the above reaction. First of all, it is electrical conductor. If you said it can conduct electricity or it allows charge to move through it, you get the mark for electrical conductor. The second thing that you need to indicate is that it's not going to react with anything that's in the solution. So if you wrote unreactive, you'd get the mark. If you said that it is inert, you get the mark. If you wrote out it does not react with anything, you get the mark. And lastly, this is one that I'm tending to favor recently, but I've never actually seen done in an exam, is it's a very weak reducing agent. So it's something that's going to, if anything happens to it, it's going to be reduced, but it's a very weak reducing agent. So that's why I might accept this one, but I'm just warning you, I haven't seen that before. So let's quickly ask who got all 4 of those correct. Anyone? Well done. I think the one that might have lost you some marks was the platinum uses. I'm pretty sure some of you got one of the 2, but you didn't maybe think of the obvious one about conducting electricity. Sometimes it's glaringly obvious, and then when you think about it afterwards, you realize you really did know it, but you forgot. All right. We're now going to carry on with part 8.3, where it says, what is the name of component Q? That over there is component Q. What is the standard reduction potential of the XX2 half cell? Now, I know this immediately freaks people out, but you must just go and remember that you've got that value over there, okay? And you need to think practically which way round you're going to get that voltage. So remember here, your equation is that the E theta cell is equal to E theta reduction minus the E theta oxidation. And the theta stands for standardization. So this theta is what tells us that we're going to have our temperature, pressure, concentration that was mentioned. Please note you could also write E theta oxidizing agent minus E theta reducing agent, or E theta cathode minus E theta anode. All of those are acceptable. So you're going to try to work backwards to work out what the standard reduction potential is of this half cell. That is a difficult question, potentially. And then what is the half reaction that takes place at the cathode? You'll note here that the first problem that you have is you don't know if hydrogen is your anode or your cathode. So I would play around a little bit with putting it in the different positions, seeing whether you get a voltage and seeing whether you can match that voltage to something on the table. All right. Okay. You may also find here that the order that we've written in this may count, but I'm not certain if it does. All right. So I'm going to quickly pause that and give you a chance to answer those questions, bearing in mind that short of the first one, they're a lot trickier. Go for it. Actually, I've just changed my mind. As I started to try to put in values, it becomes very obvious which way around things are going to go. Okay. Is anyone else having the same problem I am? Am I being really silly?
I'm also having a problem.
I'm having a big problem. Okay, so I'm glad that we're all having a problem together, because I'm suddenly looking at this and realizing that the big problem that I have is that nothing is going to give me 0.31 volts. This was an exam paper that was used in an exam. Shock and horror. Okay, so just so you have an idea, if we use 0.31 volts, my hydrogen is going to be 0. So I know, so we're gonna bear with this, and we're gonna breathe in and we're gonna breathe out. We're gonna realize that there was probably a mistake. This was probably a very silly typo, although I can't imagine how a typo like this would have gotten to an exam, because this is going to be 0. Our cell potential is going to be positive 0.31, and that is either going to be 0 minus a value, or we could go the other way around. Positive 0.31 is going to be a value minus 0. Either way, hydrogen is one of the half cells. So that means that we're either looking for minus 0.31 or plus 0.31. And I cannot see that. If I look there, and I actually went to go and check in case I'd got the table wrong, and there was another table that had more, and there's nothing. So what I suspect, if you look here, there's nothing there, and there's nothing there. So we're going to have to quickly just change this question, or otherwise we're going to have big problems. So I'm going to change this value. Okay, well, actually that's true. You're 100% true. Okay, sorry. There was a question that was just posed that I think is actually very smart. It said, do we actually need to be able to name X or just give it cell potential? So I think we're actually going to take that stance right now, just in case anyone was in the same position. Thank you. That was a good idea. Is that if we look at this, the standard reduction potential of the half cell, and I'm going to presume here that for me to get a positive, it could either have been negative 0.31. Okay. In fact, we were told here, I lie, we were told additional information. We were told that that was positive, and we were told that that was negative. Okay, so if the electrode is positive here, that means that it is the cathode, which means that it is my reduction half reaction. I'm cheating a little bit and jumping ahead, but I think this one's already floored me a little bit. So if it is reduced, that says that this must go this way, which means that the other one should have been over there, but it doesn't exist. So this is going to be my oxidation half reaction because it happens at the anode. Now, I think this question, as much as it's floored us, is a very good example of what happens quite often in the exam, where you suddenly get an idea in your head, as I did, and I think most of you did, that it's got to be on the table. And it wasn't on the table. And then we got very angry. So here we know that if we do it this way around, it's got to have that order. Okay? So that's probably where a lot of people went wrong, is that they missed maybe that it didn't have to be on the table, and they also potentially missed the negative and the positive. So our standard reduction potential of the X2 plus half cell must be negative 0.31 volts. All right, now I'm going to ask a very brave question. Did anybody get that completely right on their own? Because they weren't burdened down by the fact that they were expecting to see it on the table. All right. I actually am a little bit jealous if you did that, because I think sometimes people that overthink it go into a panic instead of just realizing that you could, as somebody pointed out, you could just ignore that you didn't know what it was and you couldn't find it. Then you were asked to write down the half reaction that takes place at the cathode. Now, we're really lucky here. We'd have figured out that the cathode was the positive. I must be honest, I didn't see that plus and minus until it came to me being about to say, oh, well, you could do it either way. And then I suddenly thought, no, you can't do it either way. So can I ask everybody right now, I'm going to give you a quick chance before I tell you the answer, to write down the half reaction that takes place at the cathode. Go for it. All right, that is about as long as it should have taken you to get to an answer. So if I do this over here, I know that my cathode is where reduction takes place. Therefore, it's the hydrogen reaction, and it's 2H plus, picks up 2 electrons and goes to H2. You did not need to put in the gas at the end, but it's not a bad idea to write out exactly what is here. There is one thing that you couldn't have done and still got the mark, and that's that you couldn't use a reversible arrow. If you put in both sided arrows, you lose the mark. You've got to commit to it is going that way, or read the oxidation half reaction properly. All right, so I'm hoping after that little hiccup where I kind of thought, many of you may have also gone, that you now understand where we're up to. Now it gets even more interesting. We still don't know what X is. We're kind of breathing in and out and going, it's all right, we don't need to know what X is. Now we're told that the hydrogen half cell is taken away, and instead of it, we're putting in an M into M2 plus half cell, and that the notation of this cell goes in this order. This now may tell you what your anode is, what your cathode is, what your order is on this table, okay? You were told that the initial reading on the voltmeter is now 2,05 volts. Please bear in mind, you still know the cell potential of the XX2 plus cell, even if we couldn't find it on the table, all right? So you are asked to identify metal M and show how you got your answer. As a hint, 5 marks. You've got to do a bit of work. And then the next question asks, is the cell exothermic or endothermic? Ladies and gentlemen, I'm just going to pause and I'm going to give you a chance to think through all of that. Try and come to an answer for both of those. Please remember, you can probably answer the second question even if you can't answer the first question. Okay, so go for it. Good luck. This one's a little bit abstract. It's supposed to be tricky. All right, please, when you get to an answer, give me a thumbs up. As a hint, be very, very careful about making sure that you read your cell notation in the correct direction. And that tells you whether X is being oxidized or reduced, which in turn tells you whether M is being oxidized or reduced, which in turn tells you which order to put things into your reaction, which in turn should give you an answer that you can find on the table. You should find a value for M on the table, and it's easy to see that it's the correct thing. Just be careful with positives and negatives, otherwise you may not be able to find the correct thing. All right, so far I've had 2 people get it. I think I'm glad I picked this question. I think this question may have been one of the ones that put me off redox years ago, because it's a nasty one. Okay, good. Good, good. I think we've got so far 6 of you who've got it, well, are happy with it. I think I'm going to give you 7. Good. Just a little bit longer, because I think once everybody's got it, then or close to it, then we'll be able to go. Okay, cool. And I'm getting answers. All right. I think most of you have got it so far. So also somebody posted the answer, so I'm now going to go and share it. What I did was I looked at the fact that it said M to M2 plus gives us X2 plus to X. Now remember, that tells us that M must be here and M2 plus must be there, because this is going to be your OHR and this over here is going to be your RHR. RHR I knew was negative 0.31. Now, unfortunately, if you got this answer wrong, even if you plug this value in here, you could get some of the making up marks, but you probably wouldn't find that it corresponded to an element that went from a solid to a 2+ ion, and you definitely wouldn't find it gave you magnesium. If you got an exact right answer, then you could get a mark, but unfortunately, you're unlikely to get all of the marks here if you'd messed up in 8.3.2. Positive marking and all, you're still not going to be able to do it. So I realized that the reaction must go there, there, there. To make my life easy, I said negative 0.31 is somewhere there. So I'm just going to pretend it. I'm going to kind of move things across and slide it in because it makes it easier for my brain to comprehend it, which means that it probably does for some of yours as well. So from there, I didn't know where M was. So I just randomly kind of said, well, it's somewhere up here. That helped me to remember that when I did my E theta cell, it was reduction minus E theta oxidation. My E theta cell is 2,05. For our Voltaic cell, it will always be spontaneous. So this will always be positive. So I put in positive 2,03. Then I said, well, it's going to be my E theta reduction, which is going to be, in this case, that value, which is negative 0.31, minus my E theta oxidation, which was something here that I didn't know. Then I worked out that 2,05, this came across and became plus 0.31, had 2,36 on that side, but that was negative E theta ox. So I divided both sides by the negative, and I got my oxidation half reactions cell potential was negative 2,36 volts. Then I looked at the table and I could see that there was a value of negative 2,36 volts. That means that my answer is magnesium. Now they asked you to identify metal M, so you could have written magnesium or Mg. Please don't write Mg2 plus, that's identifying the ion and they may not give it to you. Sometimes if they specifically ask for, I mean here instead of saying material M, they may actually have said to you identify the anode and you'd have had to be very specific that it was magnesium. Last part of this question was, is the cell reaction exothermic or endothermic? Any reaction which gives off energy must be exothermic. So as a rule, anytime you have a voltaic cell, it will be exothermic. Anytime that you have an electrolytic cell, which we haven't yet done together, but electrolytic cells are endothermic. They require energy. Voltaic cells are exothermic because they give off energy. All right, now, unfortunately, I think there is one last question hidden underneath here. So I'm going to just quickly scroll down to it. And I'm going to clear all of the other drawings before we go back to asking everybody how they did. And the question says, the reading on the voltmeter becomes 0 after using the cell for several hours. Give a reason for this reading by referring to the cell reaction. Does anybody know the answer? Why is it that after a certain amount of time, our voltmeter reading drops to 0? From 2.05, it'll drop to 0. Anybody know why? Okay, it reaches chemical equilibrium. All right, so as soon as we get a 0 value, thank you for that answer, it reaches chemical equilibrium. I would say for 1 mark, that is sufficient, okay? You may also say that the rate of the forward reaction is equal to the rate of the reverse reaction, but we all know that that's the same thing as saying it reaches equilibrium. So it's probably smarter for us to just say it reaches chemical equilibrium. And then if you really feel the need to say that the rate of the forward reaction equals the rate of the reverse reaction, you can do that as well. All right, so I'm just going to quickly at this point stop sharing for a second. I want to check in with everybody. Who found those questions very easy? Anyone? 1 person, 2 people. Well done. You guys have evidently been practicing a lot. I think I can assume safely, therefore, that the rest of you found them slightly challenging. Okay, some of them were easy. I think with all past paper questions, you should find that about 80% of it is straightforward, and then 20% of it is very tricky. I think that one became very tricky if you let it become tricky. I must be honest, if I hadn't been specifically looking for something to have a value of 0.31, and if I'd looked carefully and seen the plus and the minus at the very beginning, that probably would have been easy for me too. But I think we often miss those little things. So hopefully this will be a lesson to all of you for being observant and making sure that when you do them, you're looking very carefully and very closely and not missing anything that's particularly obvious. All right. So, ladies and gentlemen, I think everybody is hopefully ready. We're going to move on to the next question. All right. So over here, we've got another question. Surprise, surprise. Yet again, another question 8. They're all going to be question 8s tonight. And it says a standard electrochemical cell is set up using a standard oxygen half cell. Now, oxygen usually is a tricky one because it isn't on this table. However, we've got oxygen and it's in peroxide in an acidic medium. Now, I'm not going to give the game away. Part of the joy of this is having to make you find the right equation from the table. So I'm not going to tell you ahead of time what it is. So it says it's set up using a standard oxygen half cell and a standard X2 plus X3 plus half cell as shown below. The voltmeter connected across the cell initially reads 1,13 volts. Okay, so question 8.1. This is another very similar question. I think these came from two exams, one after the other. It says, besides concentration, write down one other standard condition needed for the half cell to function. I don't think I'm going to make you do that again, but if you remember, it was either a temperature of 298 Kelvin or 25 degrees Celsius, and a pressure because we have gases. Please don't talk about gas pressures when we don't have gases. So it's a gas pressure of 1 atmosphere. Now comes our challenge. I'm going to ask you to give the name of the metal that electrode Y is made of, the functioning of component Q. So what is the function of component Q? Only 1 mark. It's got many functions, only give 1. The half reaction that takes place in the anode. Please note there's a negative and a positive. They had told us which way around they go. Then I'm going to ask you, because I want us to do a little bit more in one go before I kind of intervene. 8.3, by means of calculation, identify the X2 plus and X3 plus ions. Please note 1 mark for each ion. Don't just tell me what X is or you lose 2 marks. And 8.4, give a reason why the voltmeter reading will eventually become 0 volts. Kind of similar, but we're going to quickly do it. So I'm going to pause and give you a chance to do that. Please go for it. I assume you've written down the E theta cell reaction from the last time I gave it to you. E theta cell is E theta reduction minus E theta oxidation, no abbreviations. All right, please give me a thumbs up as soon as you're done with that. Okay, brilliant. Well done. I'm hoping that the rest of you are still working good and getting towards an answer and you haven't just given up because it was tricky. Okay, now I'm just quickly asking the important question. Is there anybody who's totally lost? If you're totally lost, you need to look at the positive and negative electrodes and decide which one's the anode, which one's the cathode, and you need to work from there. I'm obviously talking about the hard 5-mark question, not the slightly easier, shorter questions. All right, does anyone need me to wait any longer? If you want to, you can just quickly give me a thumbs up and that'll mean stay and wait for me. Okay, maybe some of you gave me thumbs up before I started. All right, so if I continue now, the name of the metal that electrode Y is made out of is platinum. It has to be platinum because we've got 2 aqueous ions in solution. There is no, we don't know what they are yet, but they're 2 aqueous ions. So we're going to need our inert electrode. So Y must be platinum. Okay. The function of component Q is our salt bridge, and it is either to complete the circuit or to maintain electrical neutrality, or you could say to keep the 2 half cells separate. Any of those is acceptable. All right. Ooh, I left off a question. I'm going to have to quickly fill it in. The half reaction that takes place at the anode is my oxidation half reaction over there, and it's where oxygen reacts with H2O2 in an acidic medium. As soon as they say acidic medium, you need H plus as part of it. So if I look over here, H2O2, H plus, and O2 are all there. Also, because this is at my anode, I know that I must read it as an oxidation half reaction. So this reaction over here is H2O2. Hydrogen peroxide will get oxidized to produce oxygen plus 2H plus 2E minus. You'll often see that if you need an H plus in solution, like an H plus there, or like an H plus there, or an H plus there, they sometimes say that it's acidified. I actually need to come back and discuss those ones with you in just a second when I've done the rest of these. by means of a calculation, it says identify the ions X2 plus and X3 plus. So I said here E theta cell is E theta reduction minus E theta oxidation. My cell potential value, where is it, was given as 1,13. So 1,13 is equal to E theta reduction minus negative 0.68. The reason that I knew that this was negative 0.68 is that I knew that it was oxidation because it happened at the negative electrode. So then what happened is this value got taken across and it became 1,81. I went and found 1,81, which is over there. And fortunately, it ends up giving me two ions, one with a 2 plus and one with a 3 plus charge, which makes perfect sense. All right, if it didn't make perfect sense, I'd get worried. Okay, please, just an important thing, if you ever put in a reversible arrow here, this was just a question that was asked, if you ever put in a reversible arrow there, it takes away your mark. In this case, since it's 2, you may lose one of the 2, but I suspect they may also penalize you to lose both of the 2 if they're doing an all or none. So whenever you read an OHR or an RHR, commit, write it in the direction you want it to be in, and put the arrow in the correct direction. So here, I wanted it to be oxidation, so I wrote down everything as I saw it from right to left to make sure that it was correct. All right. So here you had to identify X2 plus and X3 plus. If you didn't have both of those written as those, you wouldn't get the mark. If you were very excited and you then said therefore cobalt, unfortunately, once again, you don't get all of the marks. And I can vouch for that. They've done it relatively recently. It felt a little bit unfair. There's no allowance for it. It's 1 mark here and 1 mark here. Saying cobalt, we're thrilled that you got there, but you're still only getting 3 out of 5. Okay. And then lastly, give a reason why the voltmeter reading will eventually become 0 volts. It's because the equilibrium is reached. If you want to say something differently, you could say that the concentration of H2O2 decreases and the concentration of CO3 plus decreases. But the real truth, and this is what we do want you to know, is that 0 volts means that we're in equilibrium. That's one of the things that we'd ideally like your brain to automatically connect so that it's easy for us to give you the marks there. All right, so I'm going to quickly stop sharing. Who found that one was a little bit easier than the previous one? Anyone? Okay, good. May also have been that you're just getting a little bit more used to the idea. You're getting used to the idea. Okay, can I ask one last question? And I know not all of you have done this in school, but how do these questions compare to the ones that you've been practicing so far? Who finds that the examples that I've picked are a little bit more challenging, or they compare with the more challenging ones? I did aim to make them slightly challenging. Not quite your easiest version. Okay, one person's been practicing. Yay, 2 people, 3 people. Okay, brilliant. Okay, let me quickly just scroll down before I share my screen. Okay, let's keep going. All right, so here's our next question. It's a tiny bit blurry, so I'm hoping that everybody can still read it clearly. If you can't, you're going to have to shout and let me know. So the question says, learners set up an electrochemical cell shown in the simplified diagram below using magnesium and lead as electrodes. They don't tell you which one's which, but we know we've got magnesium and we know we've got lead. So as a hint, pick them off on your table. Nitrate solutions are used as electrolyte in both half cells. So we'll have magnesium nitrate and lead nitrate. What type of reaction takes place in the cell? Easy question. Hopefully you get it. 8.2, which electrode is magnesium? Give a reason for your answer. Remember that this should be spontaneous. They didn't actually say it would be spontaneous, but 2 separate containers, we know we're dealing with a voltaic cell. Then I'm going to ask you to write down the standard conditions under which the cell functions. You'll notice they're asked every time. That's because in every exam paper, we're going to test you a little bit on it. The cell notation, remember that's our specific layout, and then the name or formula of the oxidizing agent in the cell. They're also going to ask you to calculate the initial EMF of the cell under standard conditions. I'm going to ask you to do all of those first 8, and then we're going to discuss 8.5 together afterwards. All right. So I'm going to pause sharing and give you a chance to fill in all of those answers. Go for it. Good luck. Maybe even do it so that you can get a mark at the end of the side of 15 that tells you where you're up to. Okay, when you are done, please give me a thumbs up. Okay. Good. Good. All right, I think that's the majority of you. Hopefully those of you that are still busy are nearly there. Okay, good. All right, so I'm going to share again. Now, what you had to do here, and I know I've got a lot of writing here, so just bear with following what I'm doing, not reading ahead of time, is we're going to go through them one at a time. What type of reaction takes place it is a redox reaction. We know that. They draw us this picture. It's not going to be any of the others. Please note a neutralization reaction, just for your own benefit, occurs between an acid and a base. A precipitation occurs where we form an insoluble solid. So if we'd done lead, I think lead and sulfur form lead sulfide, which might be insoluble. There are a couple of lead salts that actually form that may be precipitation. Then would make a solid white powder or a solid colored powder at the bottom. None of those happen. This setup, you know it's redox. Which electrode is magnesium? Give a reason for the answer. So at this point, I had to go and circle magnesium and lead. Remember that both of their electrolytes were present, and then figure that for it to be spontaneous, the reaction that's higher up on your table 4B would be oxidized, and the one that's lower down would be reduced. Then remind myself that this was oxidation half reaction, that was reduction half reaction. If it's oxidation half reaction, it occurs at the anode. The anode is negative in our voltaic cell. Please note, anode becomes positive in electrolytic, it changes sign. Be ready for it. Over here, I have my positive cathode for my RHR. So I then went and said the question was, which is magnesium? Magnesium is negative, and I went and wrote it over here, double checked and said that it was P. Please don't write here positive or negative, that wasn't the question. You were then asked to give a reason for your answer. Now this was for 2 marks. I assume that there's 1 mark for P and 1 mark for the other side, but what I went and said is that the negative electrode is the anode, magnesium is oxidized. So I probably gave them more information than I needed to, but I think I gave them enough to be sure that I got the mark, and that's what I was going for, was getting the mark. All right. Next bit was to write down the standard conditions under which the cell functions, the temperature of 25 degrees Celsius, and a concentration of 1 mole per decimeter cubed. Please note, I'm always tempted to say concentration of electrolytes of 1 mole per decimeter cubed and pressure of gases of 1 atmosphere, rather than just concentration and pressure. You were then asked to write the cell notation. If you remember what I told you, it's this one first, / this one. Double / to represent the salt bridge, this one / this one. So it's Mg solid / Mg2 plus aqueous, double / Pb2 plus aqueous / Pb solid. Please, if you wish, you may choose with aqueous to write in there 1 mole per decimeter cube. Right at the end, you may even write comma 298 Kelvin, but we usually leave those little bits off because they usually don't give you marks for them. They also, if you do them wrong, you can potentially confuse the examiners and lose marks. All right, the name or formula of the oxidizing agent in the cell, well, the oxidizing agent is the substance that is reduced. And if you look here, your starting material for the reduction half reaction is Pb2 plus. Please note, if you wrote Pb, it is wrong. So it said name or formula. So you could actually also have said here the lead to iron. But if you just said lead, it's wrong. You were then asked to calculate the initial EMF of the cell above under standard conditions. So our initial EMF is E theta cell. It's going to be E theta reduction minus E theta oxidation. So it's going to be negative 0,13 minus negative 2,36, which gives me a value of 2. Remember, the minus makes it a plus. So I got 2,23 volts. Also, a little thing that people forget, don't forget your units of volts. You lose the marks. All right, can I quickly have a show of hands? Who got majority of that correct? Fantastic. You can see that there's a question. All right, so there's a question if they ask for the overall equation, should we include the spectator ions or leave them out? I would say if they, I mean, here we weren't actually asked to do it. If they had asked us, there's nothing to stop us from putting in the nitrates. NO3, sorry, that should just be a minus and NO3 minus. So we could, if we'd been asked to do the overall reaction here. In fact, maybe we should quickly do it. Your overall reaction would be your OHR read that way, your RHR read that way. I find that if I skip steps, I mess up. So this isn't part of your question, but this would be magnesium going to magnesium 2 plus 2 electrons. and your RHR would be Pb2 plus, picking up 2 electrons and going to Pb. Since we got the same number of electrons, we don't have to multiply anything. So here we'd have magnesium plus Pb2 plus going to magnesium 2 plus Pb. And then yes, it's tempting and there's nothing to stop you. That would be your net ionic. And I don't think they'd penalize you if you didn't put in your nitrates and make this Pb brackets NO3 to arrow Mg NO3 2 plus Pb. In fact, I'm telling you with certainty, when I was in school, we did have a thing where you'd have to be able to put your spectator ions back in. But they took that out of the syllabus quite a long time ago. So I think you're safe to just write that bit down. However, having said that, if you wrote that step down and then you wrote that afterwards, I don't think you'd be penalized for putting in spectator ions. So putting in spectator ions, not an issue, they'd ignore it. But yeah, I don't think you'd be required to do it. All right, last little bit here. How will the voltmeter reading change if the size of the electrode P, which is over here, is increased and the initial concentration of the electrolyte in the half cell is increased? So as a hint, you can only write down increase, decrease, or remain the same. I'm going to quickly pause while I give you an opportunity to commit to an answer. All right. All right, ladies and gentlemen, let's quickly check with everybody. Who's got answers for both? Who's a little bit confused with the first one? Now, I have a little rule when it comes to how you deal with things where it's a little bit confusing with the first one. And that rule comes in if I didn't care about what something was before, am I suddenly going to have a different answer if it's bigger or if it's smaller? So if I never cared what it was in the first place, how do I know that it wasn't already the bigger value in the first place? Think about that. So if they ever go and say, how does this change if this changes? And you go, well, I didn't really care about that to start with. Suddenly you start caring about it because you're like, oh my gosh, I wonder if it actually is important. Please don't get caught up. If it wasn't important to begin with, it probably doesn't become important when the question asks you to do it. That's a big hint. All right. So let's go and have a look at what our answers are. So the first one, it says, how will the voltmeter reading change if the size of electrode P is increased? I'm going to ask you, who said increases? Who said decreases? And who said remains the same? Wow. Okay, that was a bit of a delayed response. The answer is remains the same. You never cared how big the electrodes were at the beginning. If the electrodes are suddenly bigger, it's not really going to make a difference, okay? Now, realistically, I know if you sit long enough, you could probably come up with 1,000 reasons why if the electrodes are bigger, there's more surface area, and therefore more can happen, blah, blah, blah. But we never cared about how big they were to begin with. So our voltmeter reading at the beginning wasn't dependent on how big the electrodes are. It's not suddenly going to become dependent because we care about it. So our answer here remains the same. The next bit asked about the initial concentration of the electrolyte in half cell B. So you've got to go and carefully look at half cell B. Half cell B is our positive electrode, and it's the lead to lead 2 plus. Specifically, it's the, sorry, wrong way around. It's the lead 2 plus to lead. That means that lead 2 plus is a starting material. Please be very careful. I must be honest, if they asked me if I changed magnesium 2 plus, I'd say, well, magnesium 2 plus doesn't really affect much. It's it's something that we're going to make, not something that we're going to start with. So what you should look for here is that if you've got something that is your starting material and we increase the concentration, that's going to change our reading. Because remember, we initially specified that it had to be 1 mole per decimeter cubed. Suddenly, if it's going to be bigger, then we're going to have more chemicals to react. We're going to have more electrons being, more energy being transferred, more chemical energy turning into electrical energy, and we should end up with an increase in our voltage. Can I quickly ask who went for increase as well? Okay, good. Please don't I hope my little thing about if you didn't care about it in the first place, this one you did care about in the first place because you were very specific about what it was. All right. Ladies and gentlemen, I know we're a little bit short on time, but I think we're going to stop because I don't think we're going to get through a whole question in just 1 minute. All right. So I hope that made a lot more sense to you in terms of what kind of questions we're likely